Hi, my name is Casey Wade. I'm a chemistry professor at Brandeis University. Today my graduate students and I would like to tell you a little bit about the research going on in our laboratory. Before we start, I want to introduce each of the graduate students who are helping me out today. This is Katie B., second year graduate student from Massachusetts. And running the camera behind you is Ben Reiner, a fourth year graduate student from Connecticut. So the research in our chemistry lab deals with the synthesis of new molecules and materials. In many ways, we're like chefs that are designing new recipes or new dishes. And the tools that we use are actually pretty similar to the types of tools that you use in your kitchen. For example, we have spatulas and measuring cups. Okay? But our specific expertise is the synthesis of inorganic molecules and materials. This means that generally we deal with metals. Metals can be found in many forms. You're probably most familiar with elemental forms such as copper pennies or iron nails, but metals can also be found in other forms such as salts and minerals. For example, sodium is a major component of table salt, and aluminum is actually a major component of alum. You may not be familiar with alum, but it's actually used to make pickles crunchy. Metals are also found in organic and biological materials. For example, your blood is red due to the presence of iron, and the major component in vitamin B12 is cobalt. So one of the types of materials that we work with in our lab are called metal-organic frameworks. As the name suggests, metal-organic frameworks contain both metal components and organic components. So here I have a generic structure of a metal-organic framework. Right? And in this structure, you can see yellow balls. These are the inorganic, the metal parts of the structure, and the gray linkers that join them together. That's the organic part. And so when we synthesize these materials, we combine the metal component and the organic component in solution, and together they self-assemble to form a porous structure. That's right, a porous structure, like a sponge on the back of your sink. And in fact, metal-organic frameworks behave a lot like the sponge on the back of your sink. They can actually soak up molecules. And so if you look carefully at the structure, you see that there are spaces inside. These spaces can actually absorb or soak up small molecules. So today, what we're going to show you is the synthesis of the metal-organic framework that we work with in our lab. The framework is called copper 135-benzene tricarboxylate. I realize that name is a bit of a mouthful, so instead of using that, we're going to call it by its more colloquial name, HKUST1. And with that, let's go to Katie, who's going to show us how we actually make these materials. Our ingredients for making HKUST1 are copper nitrate, salt, a solid organic compound called trimesic acid, water, and two organic solvents, dimethylformamide and ethanol. That's right, the same ethanol found in your favorite adult beverage. So our first step in making a metal-organic framework is to measure out the correct amount of each ingredient. And so we start by measuring out the solid ingredients by mass on an electronic balance. And you can see here, Katie is measuring out the correct amount of the copper nitrate salt. And she double checks to make sure that the reading is right. And now she's going to use the weigh paper to transfer the copper nitrate to a glass jar. And the glass jar already contains our trimesic acid, so we have both solid ingredients in the container that's going to be used to run the reaction. So the next step is to add the solvent, the liquid reagents. She starts by adding dimethylformamide. You can see it's a clear, colorless liquid. And then next, our favorite molecule, ethanol. And finally, she adds a little bit of water to the reaction. And you can see now that the mixture is sort of cloudy, turning a little bit blue. The blue color, again, is due to the copper salt. But in order to get everything to become a homogeneous, a clear solution, we need to mix it up. Right? And it turns out we don't have a KitchenAid mixer available to blend everything. So instead, we're going to use a stir bar, a magnetic stir bar, and a stir plate. So Katie will cap the jar, put it on the stir plate, and let the mixture stir for 5 or 10 minutes until everything's completely dissolved. Okay, we're back. So now, after stirring our jar, or heating our reaction mixture for about 5 or 10 minutes, you can see that we have a homogeneous blue suspension. And so now we need to heat this reaction mixture to 85 degrees C, or 185 degrees Fahrenheit, in order for the organic and inorganic components to come together and form the solid metal-organic framework. So in order to heat this jar, we're going to use an oven. The ovens that we use aren't really that different from the type of an oven that you would use at home. Although you can see We have our row of ovens here. They have fancy digital displays so that we can precisely control the temperature at which we heat our reactions. And also, they're reinforced in case anything bad like an explosion happens. Okay, so again, the last step is to put the reaction mixture into our oven. And we preset the temperature for 85 degrees C. And you can see now that it's heating up at 47, and it'll keep going. And we'll leave our reaction mixture in the oven overnight. And tomorrow, we would have a nice blue solid that precipitates. That is our metal organic framework. But in the spirit of any good cooking show, we've already carried out the reaction, so we can actually show you what this will look like in the morning. So after cooling, you see that there's a dark blue precipitate in the bottom of the jar. That is our metal organic framework. So the next step would be to filter this, collect the solid and dry it, and then we have metal organic framework for future experiments. And so with that, thank you for joining us today, and tune in again for more experiments from the Wade Lab.